Hello, this is Dr. Lori. Welcome to this discussion on converting graphs to numbers. So I always like to think about doing things in reverse because I think it really helps people kind of grasp on to some of the more fundamental concepts in a different way. So the more ways you can think about something, the better. And so let's take a look at thinking about what happens when we convert graphs backwards into the numbers that they really represent. So this first example is of a histogram, and it is symmetrical, and so we would call that normally distributed. And one of the features of something that's normally distributed is that we could draw a line right down through the center, and it would be a mirror image on the left versus the right. And so it really should be a bell-shaped curve if it's truly normally distributed. It should be symmetrical, and there are three things about this normal distribution that really define it as being normally distributed. And the first one is exactly that whole idea of it being symmetrical and bell-shaped is the shape. And so if you have something that's symmetrical and has this bell shape, then that's what we call normally distributed. The other two features of it are defined by location and spread. And those are, the location is the mean, or where it is centered. What is that location in the middle? And the spread is typically expressed as standard deviation. And that's kind of, I'll give sort of an approximate location for those. So you have a little tiny bit left here in the tails, but plus and minus 2 standard deviations is approximately the width of the curve. Now what that means is that we can do a few things with this. Once we know these three things, we're able to graph that particular information. But what that also means is that if we know the shape of the curve and its mean and standard deviation, how far it is between here and here, which if it's symmetrical, then each of these four sections would be the same, then we can take the graph and we can convert that back to this same information. So what I like to do is give you a helpful hint, and that is a lot of people have a pretty easy time finding the mean. And so if you have this and it's maybe along a particular scale, and it has gradations, assume they're even, you would just literally find the point that is the very highest and track that down, and that would be your mean, whatever that is along the scale, whether it's 12 or 20 or whatever that number is. But people have a little bit harder time guessing about the standard deviation. And so here's a pretty okay rule of thumb. It's not exact, but it's a close estimation. If we were to take the highest value, that's going to be somewhere here, and the lowest value and subtract them, we call that the range. Highest minus lowest equals range. And so range really is a number. It's not a bracket that has the lowest and highest numbers listed in it. If our highest number here was, say, 20, and our lowest number here was, say, 10, these gradations do not make sense if that's the case, because I've just randomly drawn them on there. But if it's 10 and 20, then the range would be equal to 20 minus 10 equals 10. So the range is equal to the difference between the two. If we were to take that range and divide by approximately 4, that will give us an approximation of our standard deviation. And if you look back at our picture, you can see why. 95% of this population or sample, depends on what your your normal curve is of, is encompassed by plus or minus approximately 2 standard deviations. The range might be slightly higher than that, but it's still a pretty good guess. So in this case, our middle point would be 15, and our standard deviation would be 10 divided by 4, which is about 2.5. So that is a way that you can take a picture and turn it back into the numbers that really define it. So in summary, a histogram is defined by shape, location, and spread, whether it's bell-shaped or not, where it's located along this continuum, and how far spread out it is. If the spread numbers were to change but the mean didn't change, then it would just become wider or narrower. And if the location changed without the spread changing, it would just shift to the right or to the left. So those are our 3 defining features. So kind of keep those in mind. This next example is of a histogram that is not normally distributed. And in this case, you can see that it has right skew because it's as if somebody took hold of this right-hand side and pulled it to the right. Don't let the location of the peak confuse you. Right skew is the direction of the tail. So here we have a distribution that is right skewed. We would have the same kind of discussion if it were left skewed, just in a different way. And the kinds of things that I want to point out to you are how that affects those things that are shape, location, and spread. So if we were to have this move off to the right, then our peak, or the place that it would touch, like the tangent line, let's say, is right here. What ends up happening is the mean gets pulled along with this point, and the reason for that is that the area under the curve over here on the right hand side needs to equal the area under the curve over on the left hand side in order for this to be the dividing point that ends up being the mean. So you can see what happened is, as we were pulling the tail over here to the right, the mean also got pulled over to the right a tad. A lot of people would label this point right here the mode. Depending on how things are measured, that can be a little bit deceptive, but it is supposed to be the highest point of that particular curve. The other numbers that get sort of pulled along the way are median. Median gets pulled less because it's less influenced by extreme outliers that might be out here or even like way out here. So the median is the middle point of data, and so the median would also be pulled over here to the right, but not nearly as much as the mean. And so if you're looking at a curve like this, you need to find the mode, or find that tallest point, the apex, and then kind of, if you're trying to estimate, remember we're trying to estimate from a histogram and come up with numbers, then if you were looking along whatever the scale is, if our highest point is here, then our mean is going to be somewhat to the right. And it depends how skewed it is and how many outliers and how severe they are, but it's always going to be moving here in the direction of the skew. So if your skew is to the right, the mean will move to the right. If the skew is to the left, the mean will move to the left. And then the same kind of rule applies to the, if we're looking at either median or standard, or median and mean, or with standard deviation and interquartile range, is if we take our highest not outlier value on each end and divide by 4, that should give us approximately either our standard deviation or the interquartile range. It's not an exact science, but if you think about this particular shape, remember how with the box plot we're trying to split things into 4 equal groups? We're going to end up with about half of that range being the interquartile range. So the highest minus the lowest. Some people would argue, depending on how far out outliers are, whether you include them in this value or not, and that's where you kind of have to use a little bit of your judgment. Now I've looked at here at a histogram that's not normally distributed, and normally we would not use a non-normally distributed histogram to come up with the median, nor would we use it to come up with the mean. So let's take a look at what we would do, and that would be more like a box plot. So if here we have our box plot, and maybe down here on the bottom we have some kind of scale, so forth. Literally, all you do is you follow that number down and you find the numbers that correspond with the features on that box plot. And then you would be able to say what is the median, the 25th percentile, the 75th percentile, the minimum, and the maximum. So if you're trying to convert a graph to numbers, these tend to be the numbers that you would want to be extracting off of the box plot. The only other one could be the interquartile range, and that would be by simply taking the 75th percentile, that value right here, and subtracting the 25th percentile, you would get your interquartile range. You might also be asked about the range, and that's where you would take your maximum minus your minimum, and then you could calculate that simply by subtraction. And finally, last but not least, if we have our bar graph, we should be able to extract information from the bar graph and be able to convert all of these bars into numbers and percentages. And the way we can do that is that over here on the left-hand side, whatever kind of scale we have, we can follow the height of those bars on over to the left, and we can see on that scale exactly how high they are. So we're looking at the height of the bar and following it over here to the left-hand side. Now the main thing to remember is that bar graphs usually show counts. So in other words, they show the frequency of that particular category, let's say A, B, C, and D. But they can be changed so that instead of count, this number over here could be the percentages. And so depending on what you're reading, the actual numbers that are out here, you might be reading the percentages or you might be reading the ends. And so just be very careful about that. If it's given in percentages, then the bars should all add up to 100%. Whereas if it's given an n, then all the bars should add up to the total sample size. So you would be able to figure that out usually based on how it's labeled over here on the left-hand side. So that concludes my demonstration on how to convert graphs into numbers that would go into a descriptive statistics table.